Well, hello everyone. We're going to be looking at the next module here. This is about carbon, not just another element. And the sections that we're going to be looking at are why carbon, organic chemistry. You probably won't find that in your book, but we're going to cover it anyways. Hydrocarbons and reactions. The reactions can be found in the different sections in the book. I'm just going to have you try to recognize a couple of types of reactions. The organic chemistry section is going to be divided into two lectures. So let's go ahead and start with carbon, not just another element. So why carbon? We want to understand the factors that contribute to the large number of organic compounds and the wide array of structures. And we want to recognize that when we say organic compounds, we're basically saying compounds that contain carbon. And we want to recognize types of isomerism that are seen in organic chemistry. So, why carbon? There are two basic factors that contribute to the large variety of carbon compounds. And when I say the large variety, carbon-containing compounds, there's about 20 million of them that are recognized, whereas the compounds that don't contain carbon, there's about 500,000. So there's quite a few carbon-containing compounds, quite a few more than the non-carbon-containing compounds. And in general, we say carbon-containing compounds are organic compounds, whereas the non-carbon-containing compounds are called inorganic compounds. Well, one of the biggest factors of why there's so many different carbon-containing compounds is that organisms make carbon-containing compounds. There's millions of different species of organisms. And so naturally, we should expect millions and millions of different organic compounds, not just millions. I mean, with so many different species, you would expect an exponential increase in the number of different organic compounds. Why is that not the case? Well, it turns out that a lot of the compounds are shared in different organisms. The other big reason is that carbon is structurally diverse, allowing for a variety of physical and chemical properties. So let's take a closer look at this structural diversity. So here are a number of the reasons for the structural diversity of carbon. First of all, carbon is tetravalent. It makes 4 bonds. The other elements that tend to make 4 bonds are those that are in the same group, so that would be silicon. And we're looking at things that are non-metals that make covalent bonds. So silicon also makes 4 bonds, but one of the reasons for the structural diversity is carbon is tetravalent. Carbon can also make single, double, and triple bonds very readily. Silicon cannot. So that's why there's fewer silicon compounds. Carbon readily bonds to other non-metal elements. Silicon, not so much. Carbon has a variety of geometries: linear, trigonoplanar, and tetrahedral. Silicon is mostly tetrahedral, some trigonoplanar. Carbon can make carbon-carbon chains and carbon-carbon branches. Here, if I put another carbon here, you can see that I can just put carbon after carbon after carbon after carbon, making a chain, but every now and then I could branch off. And so that gives you a large variety. Silicon doesn't bond to silicon too well. Carbon makes Goldilocks bonds. This means they're not too strong and not too weak. And that's important because if you're going to have a element that is at the center of organisms, you want the bonds to be strong enough to add structural integrity to whatever the organism is, but you don't want it to be so strong that it can't react and it can't metabolize. So you've got to have the Goldilocks bond. Silicon doesn't make the Goldilocks bond. Carbon can make isomers, structural isomers and stereoisomers. Silicon kind of can too. Some carbon compounds are gas, some are liquid, and some are solid at room temperature. This is really important. I mean, if you think about it, what do? We metabolize carbon. We eat carbon-containing compounds for the carbon. And what do we do with the leftovers when we metabolize them? Well, the leftovers happen to be carbon dioxide. So how do we get rid of carbon dioxide since we're metabolizing it all the time? Well, it's a gas, so we can just breathe it out. and that's great. Whereas if you look at silicon oxide, which would be the product made from metabolizing silicon, silicon oxide is a solid. So if you're making silicon oxide all the time as a metabolic byproduct, you would need to excrete the solid continuously. So just think how horrible that would be if we were silicon-based organisms excreting silicon oxide continuously. And by the way, silicon oxide is abrasive. So if you can imagine, oh, I don't even want to imagine. So the reason I keep bringing up silicon is because silicon is in the same group as carbon, and there has been some conjecture as to silicon-based organisms. And I think it's just ludicrous because silicon does not have all the structural diversity. So luckily for us, some carbon compounds are a gas, so we can breathe them out. So you're breathing out waste all the time. Some are a liquid and some are solid room temperature. So you can have compounds that are in a liquid, so you can have reactions occurring. You can have solids, so you can have structure. Carbon's great. Carbon also can make polar compounds and non-polar compounds, which is important for liquids so that things can mix and things can perhaps not mix. And lastly, there are these things called functional groups, which we'll be looking at in a little bit. So these are a number of different reasons for the structural diversity of carbon, along with the two big reasons for why there are so many different carbon compounds, one being organisms make it, and with so many different organisms making the compounds, there's got to be a lot, and carbon is diverse. Now, I want to take a little bit of a closer look to this idea of isomers that was raised as one of the structural differences. These are compounds that have the same molecular formula, but a different structure due to different bonds or different arrangement of atoms. So the two big camps of isomers, according to our book, are structural isomers, which means you have different bonds. So if you take a look at these two compounds, you'll notice that they have the same molecular formula, 2 carbons, 6 hydrogens, and 1 oxygen. So we're looking at C2H6O, but you can see that we have a different set of bonds in each. We know there's a different set of bonds because we can simply say that, hey, in this compound, the oxygen is bonded to a carbon on the left and a carbon on the right. And here the oxygen is bonded to a carbon on the left. Well, that's the same as this over here, but it's bonded to a hydrogen on the right. That's a different set of bonds. So the structure is different. And that's what they mean by structural isomers. Now here, there are also stereoisomers, which have the same set of bonds, but it turns out the structure also does differ, but it differs in a specific way. One way is the geometric stereoisomer, which is a cis-trans arrangement. Now we saw this in a previous module where when you have an alkene, you can have a cis alkene and you can have a trans alkene. So here's an example of a cis versus a trans. You can also have that for ring structures. So here you see the 2 hydrogens are on the same side of the ring. And here, this would be cis, and here the 2 hydrogens are on opposite sides of the ring, so this would be trans. There are also something called optical isomers, which are non-superimposable images. So these guys have the same set of bonds, but the arrangement is different. Now this one, it's hard to tell that these two are different molecules. So what you should do with these guys is you should make the model of both of these, where you use toothpicks and you use different types of vegetable for the different atoms. So you want different colors for these guys. So maybe use broccoli for hydrogen. Maybe use, let's do broccoli for chlorine, cauliflower for hydrogen, because hydrogen is usually a white molecule. Chlorine is a green one in most structures when we do this in organic chemistry. Bromine is orange, so you could use a carrot. And for fluorine, we often use purple, so you could use a grape. Now for carbon, they usually use a black atom for carbon, so maybe you could use an olive. So you could use an olive, cauliflower, broccoli, a grape, and you could use, for bromine, a carrot. So make both of these and then see if you can get them to match up perfectly. And you'll find out that you can't. And so that makes these guys optical isomers. Sometimes people call them handed isomers, where you might have a left hand and a right hand. And these guys look exactly the same, except for they're not. And these guys can react with other molecules that are handed in very special ways. So for instance, if you were to take your right hand and shake someone else's right hand, it'd feel very natural. That's what you're used to doing. If you took your left hand and shook someone else's left hand, it would also feel kind of like it fits. But if you took your right hand and shook someone's left hand, it would feel kind of awkward. That's the kind of shake where someone puts their hand out like this and you kind of grab it. You grab it like paws or something like that. It doesn't feel quite right. And this handedness is called optical isomerism, and it's very important. For instance, there is a story about a optical isomer called thalidomide. Thalidomide was discovered in the 60s to prevent, or I should say 60s, thereabouts, was developed to combat morning sickness for women when they were pregnant. So this would get rid of all that nausea and stuff like that. And it turned out that women who took thalidomide had a great increased chance of their children being born with birth defects like shortened limbs. And so it turned out that thalidomide actually had two optical isomers. One of the optical isomers was the one that prevented the morning sickness. The other optical isomer, well, what it would do is it would slow the growth in fast growing tissue. And so if you can imagine, when a baby is conceived, it looks like a little lima bean, has no, very, very, very short limbs. And in a very short amount of time, the limbs grow very long compared to the body. And the one optical isomer of thalidomide actually slowed that down. So you would have children born with these shortened limbs. So here you have two isomers that are arranged differently just by the way the atoms are arranged. And one would react chemically one way and one would react chemically the other way. So thalidomide was quickly taken off the market. And there was a resurgence of thalidomide seen recently, but it didn't really come to any fruition. But the idea was that since thalidomide slows down fast dividing tissue, it was thought that, well, this might be used as a cancer suppression agent, because a cancer is a fast growing body of cells. And if you could treat it with thalidomide, maybe you could slow down the cellular growth and stop the cancer. It didn't work out too well. But thalidomide is also used to combat a certain type of leprosy. And it is used to good effect, but you have to make sure that you don't use it with a pregnant woman. Okay, so there are these types of stereoisomers. The next section we're going to be looking at is called organic chemistry. So get ready for the next video.